Hello everyone, welcome back to my YouTube channel. This is Leihua, your favorite data scientist at YouTube. In today's video, I want to introduce you guys to Bootstrap and different variants of Bootstrap. In particular, I want to introduce how we can solve big data problem using Bootstrap-like variants. Okay, sounds great? Okay, let's get started. So the focus of today's video will be on Bootstrap and its application in statistical inference. So let's start with a real interview question from a big tech company. The question is, how we take one sample from a population, how can we construct a confidence interval for the population median or any other population parameter? Okay, this is a typical setup for statistical inference because we are trying to estimate the population parameter from a finite sample. And in this case, we are trying to infer the statistical parameter using just one sample. If you are not familiar with bootstrapping or any other resampling strategies, this question may sound strange to you because how can we estimate a population parameter using just one sample, right? Because there will be a lot of variability involved, right? There's no way for us to assess the variability if you only have one sample. But if you are familiar with Bootstrap or any other resampling strategies, you will know that there's actually a quick solution to this problem, which is Bootstrap. So what is Bootstrap? Bootstrap is a non-parametric resampling strategy with replacement that requires no assumptions about the data distribution, which means we do not assume any data distribution for the Bootstrap method, and it is a resampling process with replacement. So resampling process with replacement means every single time we take a sample from the original population, we put it back next time when we try to do the resample again. Okay, related about the totally different concept is called resampling without replacement. So it means every single time we do the resampling, we do not put the data back. So this is the difference between sampling strategy with replacement and the sampling strategy without replacement. For Bootstrap, it is a resampling strategy with replacement. So Bootstrap has the following few steps. The first one is we take a sample and we treat the sample as a population. Then we do repeated sampling with replacement, and we record the estimate for the resample. The final step is because we do the first two steps repeatedly, then we can form a data distribution of the parameter. Then, based on the data distribution, we can construct a confidence interval for the population parameter. Okay, so here are just a few examples of Bootstrap in online experimentation. So let's say we want to estimate the variance, but the observations are correlated. Okay, so if the observations are correlated, then it is possible to calculate the variance using the analytical form if the observations are correlated, but can be tricky if you don't know the formula. And a quick way of doing it is just run Bootstrap. But there's a caveat, when the observations are correlated. So in later slide, in another slide, I will explain how we can do it. So the second scenario is we want to make valid inference when the underlying distribution of the population is too complicated or unknown. How can we do it? How can we do statistical inference when the population is too complicated or unknown? If it is too complicated or unknown, which means we cannot use any closed form formula to do the calculation, right? So if we do not have any closed form calculation, then how can we estimate the variance, right? So in this case, we can simply use Bootstrap to do it. Okay, so but let's look at some caveats and different variants of Bootstrap. So the naive implementation of the Bootstrap method, described above, assumes independent observations. So if the observations are correlated, or when the unit of randomization does not equal to the unit of analysis, for example, in our CTR click-through rate like example, one user may have multiple clicks. So how can we estimate the variance when there's a dependency? So there are a few alternatives. The first one is we can solve it analytically, right? So there's a methodology called delta method in statistics, which allows you to estimate the variance when there's a correlation between your numerator and denominator for racial metrics. Okay, and also we can do it computationally, and we have a special variant of Bootstrap called block Bootstrap. So we can apply this method to calculate the variance for racial metrics or for CTR. Another common criticism of Bootstrap is it is computationally demanding. The time complexity of Bootstrap is O(n) to the power k. N is the sample size and k is the Bootstrap iterations. So because the nature of the Bootstrap, it can scale up its computational demand quite quickly. If you, let's say, if you have 1 million user and you want to do the Bootstrap iterations 1,000 times, you can see the computational demand will be huge for such a reasonably large sample size. So the naive implementation of Bootstrap cannot be applied to big data, and we need special variants of Bootstrap to apply it to big data. And here are just a few examples. We have Poisson Bootstrap. We have Bag of Little Bootstrap, BLB. BLB allows us to run the Bootstrap in parallel. And also we have data compression, which is the process to reduce the sample size from n to a fixed number of data. Then we apply the Bootstrap process to the fixed data set. Okay, so in this way we can reduce the time complexity from O(n) to the power k to OK. But the downside of it is we may observe some data loss during the data compression process. So there's always a trade-off between accuracy and computational demand. If you want to increase accuracy, the computation demand will be also huge. If you want to reduce the computation demand, then the accuracy will be decreased as well. So as data scientists, we need to find the right balance between these two objectives and make a reasonable trade-off. All right. Of course, for this type of for big data problem, we always can do it analytically. There's closed form formula to calculate the variance. So for example, for 50% quantile or for 90% quantile, we can use some a formula to calculate the variance for different quantiles. So we don't have to run the Bootstrap. All right. So if you are interested in reading instead of listening or watching, then please check out my Medium blog post. So in this Medium blog post, I have listed common interview questions that you may ask. You may be asked in an interview, and also how we can implement Bootstrap in Python. If you have not subscribed to my channel, please do so, because I will update more videos on statistics and causal inference and A/B testing. So stay tuned. Bye, guys. Bye.